Hello, everyone, and welcome to today's AZO Network webinar, which is brought to you by AZO Sensors and our sponsors for today's event, OTT HydroMet. Today's webinar is titled The Impact of Dew, Frost and Soiling on Solar Radiation Monitoring and Ways to Mitigate It. And a big thank you to the team at OTT for making this event possible. My name is Daniel Azell from AZO Sensors, and I'm delighted to be hosting today's webinar. Now, before we get started, we have a few points about how to get the most out of your experience today. Firstly, the event is being recorded and we'll be sharing the on-demand link with you within the next 24 hours. So if you enjoy what you see and you've got a colleague or peer who might also benefit from seeing the content, then please consider sharing with them internally or via your social media channel of choice. If you have any technical issues that you experience today, they are normally resolved by refreshing your browser. But if this doesn't work, then send us a message using the Q&A box and our backend team will get you back up and running as soon as possible. Now, today's webinar will run as two parts, a presentation and a Q&A session. In just a moment, we're joined by Clive Lee and Victor Casella, who is in just a moment will start the webinar with a presentation before we open the floor for the Q&A. So if at any point during the presentation a question comes to mind, then use the Q&A box on the right-hand side to send those in, and we'll get to as many as we can during the Q&A session following the presentation. Any questions that we can't answer today, they'll be answered via email as soon as possible after the event. Just a quick note that if you are watching on demand, then you'll find the Q&A box on the bottom right of your screen. And again, you'll receive an answer to these questions via email. Finally, once today's webinar is over, we would really appreciate it if you could give us 2 minutes of your time to complete the end of webinar survey. This will appear once we are all done today. Now, I'm absolutely delighted to welcome Clive and Victor to get things started. Clive, over to you whenever you're ready.
Okay, thank you very much for that introduction, Danny, and welcome everybody. We're going to be talking about in this presentation the impact of dew, frost and soiling on solar radiation monitoring and what we can do to mitigate it, to reduce the effects. So I'll just say a little bit about myself. Clive Lee, I'm the Technical Sales and Services Consultant for the Kipp Zonen branch of HydroMet, and I've been with them for 25 years. And so that's in meteorology, climatology and solar energy. And Victor, would you like to say a few words about yourself?
Thank you, Clive, and thank you, Danny, for hosting this for us. Victor Casella, Sales Manager for the meteorology line in North America. I've been working with Kipp Zonen on HydroMet for the past 15 years. Prior to that, I was an operational meteorologist for the U.S. Department of Energy for almost 20 years. I did have the great pleasure to do many trips and work with Clive over our time to help develop the product lines that we have today.
Okay, thanks, Victor. So we will start the presentation. So for those of you who are not aware, we'll start off with, what actually is solar radiation, what it is that's coming out of the sun and reaching the earth. So, of course, you're familiar with pictures of the sun. It looks nice and bright and yellow, and you have solar flares on the surface. It's actually very hot. What's called the photosphere, which isn't a solid surface because the sun is gaseous, but it's the main place where the light is coming from. It's about 5,700 Kelvin, so it's pretty hot. But that means actually most of the radiation it's emitting is in the ultraviolet because of its temperature. And so if you look at it in the ultraviolet, like the second picture, actually it's in fact very brightly blue. But how much energy is actually coming out from the sun? Well, it's actually emitting about 63 megawatts for every square meter of its surface. That's 63 million joules per second. And it's an enormous amount in total. It's about 3.72 times 10 to the power 20 megawatts. And now what we measure this in, it's a radiative flux, and we measure it as a radiance, and it's watts per square meter of radiation. So it's what you would actually receive on the surface in watts per square meter. And the radiation from the sun is going in all directions, luckily. So only a small proportion reaches the Earth. If it was all reaching the Earth, then everything would burn up. The sun is actually providing about 99.97% of all the energy at the Earth's surface. There's a small amount, the remainder is actually coming in from internal geothermal energy. So the sun is driving everything. So it's driving the weather, the climate, life, every process on Earth. So we have a mean distance between the Earth and Sun of about 150 million kilometers. And the direct beam of sunlight that reaches the outside of the atmosphere is about 1,360.8 watts per square meter. That's measured by NASA satellites just outside the Earth's atmosphere. And this is called the solar constant. But of course, there is a problem with this. It's not actually constant because the Earth has an elliptical orbit around the sun. Actually, at the moment, it's about as close to spherical as it gets, or circular. The actual amount of how elliptical it is changes over time, geological time. So at the moment, when the Earth is closest to the sun, which is in January, the radiation that we're receiving at the outside of the atmosphere is about 6.6% higher than it is in June, when we're furthest away. Okay, in the northern hemisphere, it isn't hotter in January, even though we're closer to the sun, but that's because of the tilt of the Earth's axis. So there's various processes go on inside the sun. It's basically a big nuclear cycle that's going on, nuclear fusion. And they are exhibited on the surface as solar flares, sunspot activity. And these vary, typically over about something like 11-year cycle, varies a bit from 9 to 13, and causes various fluctuations in the amount of radiation that comes out of the sun. It's about 0.1% between when it's quietest and when it's most active. It doesn't sound like a lot, but because it's a large amount of energy in total, that is actually what's driving changes, particularly in the ocean currents that then affect the weather, what are called El Nino or El Nina years. It changes the ocean currents slowly. It takes a while to heat up the oceans, and it changes the weather patterns, and they follow just behind, a couple of years behind, these variations in solar activity. Now, the photosphere that's emitting is very hot. So we've got loads of shortwave radiation, ultraviolet and visible, and it takes on average about 8.3 minutes for that radiation to reach the Earth, our atmosphere. And so what's the spectrum of radiation? Well, we've got UVC radiation, which is about 100 to 280 nanometers in wavelength, and nanometer being 10 to the minus 9 meters. Then we have UVB, which is 280 to 315, UVA 315 to 400, and then the visible 400 to 780 typically, but actually that changes because as you get older, your eyesight changes, and so young children can see to about 800, older people maybe 750, but generally taken as 780 nanometers wavelength. And beyond that, you have the near infrared out to 4,000 nanometers for microns, and that's all the radiation that is arriving at the outside of the Earth's atmosphere. So then we have the effect of radiation passing through the atmosphere and getting to the surface. As it goes through the atmosphere, we've got our direct beam of sunlight, and some of it is going to be absorbed in the atmosphere by particles, by aerosols, gases, water vapor, clouds, and so some of the radiation is getting absorbed, and that's what heats up the atmosphere, of course, and heats up the clouds. And then we have light is getting scattered by particles in the atmosphere, clouds and things like that. So we end up with some of the radiation coming to the surface is a direct beam of light from the sun, and some of it is scattered by the atmosphere, the sky, and it's coming from all directions. So it's called diffuse radiation. So the atmosphere is taking out all the particles, gases and things in it, are taking out some of the energy from the sun. UVC, the very short wavelengths, those are completely absorbed largely by oxygen in the atmosphere, and there's virtually none reaches the surface. Even if you go on top of Mount Everest, you won't measure any UVC. It doesn't reach the surface, which is also why UVC lamps are used, for instance, for sterilizing water or medical equipment, because bacteria has no protection against it, because it doesn't normally exist on the Earth's surface. But it's also very harmful to people. So when you're using UVC for things like sterilization or other technical processes, you need to have a lot of protection. Then UVB is largely absorbed by the ozone in the stratosphere, about 90% for the normal strength, shall we say, of the ozone layer. And then about 10% comes down to the Earth's surface, and that's what people sometimes call the harmful UV, That's the one that is actually causing melanomas, skin cancers, and things like that, cell damage. UVA is the one that basically reddens and burns the skin, but doesn't cause fundamental damage. So then we have these components of the solar radiation. We've got a direct beam from the sun, direct normal irradiance arriving at 90 degrees to its measurement surface, DNI. We've got the diffuse irradiance arriving on a horizontal surface, diffuse horizontal irradiance, DHI, and that's coming from all directions, from the sky and the clouds. And then the total altogether is the global horizontal irradiance, everything that's arriving on a horizontal surface. And that is not just the direct plus the diffuse, because we have diffuse radiation is the same from all directions, but when the sun is going up and down in the sky at different angles, of course, it's not falling on the surface at 90 degrees to it. In fact, if you're outside of the tropics, it never falls at 90 degrees to the surface. So we have to make a correction, because when the direct sunbeam is coming in and hitting the surface at an angle, it doesn't make a circular spot of light. It makes an ellipse. It spreads out, like if you point a torch at a surface at an angle. So the energy in the beam is spread over a larger area. So as the sun goes lower in the sky, it spreads over a larger area, just like when you see shadows getting longer as the sun goes down. And so the energy density, if you like, the watts per square meter, goes down, even though in the beam it's the same. And this is a cosine function. So we end up is that the global horizontal irradiance is the diffuse plus the cosine of the angle of the direct beam. And so when it's directly overhead, that's called at zenith, and the angle is 0. And when it's on the horizon, the angle is 90 degrees. And on a clear day, when the sun is high in the sky, clear day in the middle of summer, then roughly you have about 95% is direct radiation from the sun, and about 5% is diffuse scattered radiation from the atmosphere. If you have a cloudy day, there's no direct radiation from the sun. Everything is diffuse and scattered radiation. So these are things that we actually want to measure. So when we go through the atmosphere, it's modifying the light from the sun. So the red line in the graph, that is outside the atmosphere, air mass 0. So thickness of the atmosphere is 0. And the blue line is if it's going through a thickness of the atmosphere equivalent to being at mid-latitudes, in this case, 37 degrees north, which is roughly a solar zenith angle of about 48 degrees down from vertical. And what happens is that some of the energy in the red line has gone missing. It's been absorbed by the atmosphere. So it's being absorbed by gases, particularly water vapor. And that's what is then warming it up. So it's extracted parts of that. So the spectrum of light we get arriving at the surface is not the same as we have arriving at the outside of the atmosphere. And the thicker the atmosphere, so as the sun goes down, it's coming through more and more atmosphere, it gets thicker, the bigger the effect gets. And it shifts the spectrum of the light as well. So then we have what's called the radiation balance between the ground and the atmosphere. And so for the shortwave radiation, what's coming from the sun and the sky, we have over a typical year for the entire global surface, we've got 100% of light, 100 units coming in from the sun. And then we get a lot of light is reflected back. It gets reflected back from clouds, particularly from the surface. But water is much more reflective, the oceans, and most of the Earth's surface is oceans. Also gets reflected back from snow on ice caps, glaciers, and roughly for the whole Earth over a year, about 30% of the radiation gets reflected back. So it looks like the Earth has an albedo of 0.3. About 30% of all the light goes back out towards space. Then we've got light is absorbed in the stratosphere, and in the troposphere, lower down, as we said, by water vapor and particles and things like that. So we actually end up with typically about 28% of the direct radiation from the sun actually reaches the surface, where a bit of it is reflected and some of it is absorbed, and it's warming up the Earth's surface, the water or the land. And then we've got the diffuse radiation. We have about 23% is reaching the surface. So overall, for the whole of the Earth's surface over a year, roughly 50% of the radiation from the sun actually reaches the surface and then heats it up, and some is reflected back. So then we have atmospheric and surface long-wave radiation. So what's coming out of the sun is what we call short-wave radiation. So it's arriving at the Earth's surface mainly between 280 nanometers and 4 microns. But because we've got the atmosphere is warming up, because it's absorbing energy from the solar radiation, it's warm, and so it's radiating energy, because everything above absolute zero Kelvin, minus 273.15 degrees Celsius. So everything above absolute zero is radiating energy, and it's radiating at wavelengths proportional to or related to its actual temperature. So we've got the example here in the graph at the bottom. We got our shortwave solar radiance is the red graph, and then the sort of brown colored one to the right is an example that if we have something that's at 37 degrees Celsius, 310 Kelvin, the peak wavelength it's emitting at is 10 microns, 10,000 nanometers. So this is thermal radiation. So we've got thermal heat radiation is coming in from the atmosphere because it's warm, and we've got thermal radiation is being emitted by the Earth's surface because it's also warm. So this is also part of the energy balance. And typically the radiation that we want to measure, because it varies depending on the temperature of the surface that's emitting it. So it could be coming up from very cold ice, or it could be coming up from a hot desert. But typically it's between 4.5 and 50 microns in wavelength. And so we're interested in measuring that as well. So what are the types of instruments that we're going to use for this? We're measuring all of these things as radiated flux, radiance, watts per square meter. So we have UV radiometers. They can measure UVA, UVB, or UVE, which is the one that affects the human skin for the UV index. They're all separate models. And then we also have instruments to measure direct radiance, a pyrgeometer on a sun tracker, and then to measure the diffuse radiance. So for that, we need to block the direct sun and only measure the scattered light with a pyranometer. And for the global radiance, we just have a pyranometer that's open to see the whole sky. And then the long wave thermal radiation coming down from the atmosphere and up from the surface, day and night, of course, that's a thing called a pyrgeometer. And these are all names that are defined actually by the World Meteorological Organization, and they derive from Greek. So all of these instruments, the light from the sun or the thermal radiation from the atmosphere, has to go through to a detector. And so it needs some sort of optical transmissive dome or window so that we can get light through to the detector and generate an output signal. And so what we'll come on to in a minute is, okay, what are all the things that affect that and what we can do about it? So what we'll do is we'll go over to look at our instrument portfolio. And Victor, if you could give a little description of the various products.
Thank you, Clive. And what we start off with is, I'm not going to go from left to right here. On the previous slide, we had up our range of sensors from the UV, the short wave, the pyranometer, the long wave, the pyrgeometer. And the UV sensors have a very specific market. Not only what you may understand as UV index for the epithermal to see how strong the sun is and suntans, sunburns, but also for material research, using the UV sensors for the industrial processes. Does it degrade cables, or does it affect the way the paint would fade on cars? So one application, that's where the UV sensors come in. The most popular are pyranometer, and it comes in several classes. Starting off as a basic class C, second class sensor per pyranometer, to class B, first class, and class A, a secondary standard. And as you go up in classes, the instruments become more accurate, and they go for different areas, from a meteorological network or into material testing or into research. And then the pyrgeometer used for the heat is for agricultural purposes and also for material testing as well, to see what's long wave energy is affecting the materials that's being tested. When we get up into the research side, we add our solar tracker, which Clive said earlier. We have direct radiation, diffused, and global. Also on the tracker, we have a pyrgeometer. And one of the requirements by an organization called BSRN, the Baseline Surface Radiation Network. You don't want to have the domes heated on the long wave radiation. So that's why we have a shading assembly on that to make sure that the direct sun radiation on the dome doesn't affect the thermopile inside the sensor to get the most accurate reading. So when we talk about solar research, climate change, organizations that are working with the most sophisticated instruments, they want to make sure that the data they get is at the highest accuracy. And then, Clive, we're going to continue on the slide presentations to talk about the importance for the webinar for cleaning the domes for the most accurate measurements.
Thanks very much, Victor. So, Victor was mentioning that the best pyranometers are Class A pyranometers, and there is an international standard, ISO 9060-2018. That was when it was last updated, that defines what is a pyranometer and the performance specifications for Class C, Class B, and Class A, going up in, shall we say, accuracy or reducing uncertainty of the measurement. The best ones are spectrally flat Class A, meaning that they measure all wavelengths of the radiation coming in from the sun and the sky, from roughly 300 nanometers to 3000 nanometers, and they measure it all with the same response. They measure all the radiation available. And they are capable, if they've been properly installed, maintained, and calibrated, and if the data logger or data acquisition is good enough, it's not degrading the readings, then these spectrally flat Class A pyranometers, they can measure the daily total of irradiance, the power or energy received, if you like, with an uncertainty of about plus or minus 2% compared to the world reference in Davos in Switzerland. So this is at the 95% confidence level, K equals 2, which is effectively 2 standard deviations. So this is for non-extreme mid-latitude conditions. It obviously gets a little bit bigger, the uncertainty, if you're in very hot or very cold climates. But this only applies if the dome or window is clean and there's no interruption to the radiation reaching the detector. So if we get dust, dirt, dew, raindrops, frost, ice or snow, they can really seriously affect the amount of radiation from the sun and sky that is reaching the pyranometer's detector. UV radiometers are even more affected because of the fact the shorter wavelengths in the UV radiation, around 280 to 400 nanometers, they are more easily scattered and absorbed, whereas the visible light that is the main part of the solar radiation is not so easily scattered and absorbed. There are slightly different effects on the pyrgeometers because we're talking then about thermal ones and not actually light, visible light as such. So this is a big problem. If we get a lot of dirt or dust, for instance, blowing across and it's building up on the dome of our instrument, our pyranometer, of course, it doesn't take a lot before it starts to seriously reduce the amount of light getting through to the detector. And then, of course, you don't have the correct readings. It's under reading. And one of the problems is that many places, even if they're semi-arid ones, desert type conditions almost, you have dirt and dust blowing across in the wind, sandstorms, but they still have dew in the early morning before sunrise, which is what the plants and the cactus and such like live off. So you then have a damp dome, and then the dust blows across and it sticks to it. The sun comes up and it all bakes hard, and it's then very difficult to get off, and it seriously reduces the amount of light reaching the detector. It could be 40, 50%. So in general, anything that you put over the dome that is, shall we say, obstructing the amount of light coming through is going to reduce the readings. There is one specific case where it doesn't, which we'll come on to. But if you've got drops of water, so it could be dew that is condensed onto the cold surface, or it could be raindrops, which are often a bit bigger on the surface. So those are going to scatter the light and absorb some of it, and they will reduce the readings by up to 40% until they evaporate off. And of course, if you have ice or snow, that can actually completely block all the light reaching the detector until it melts and then turns to water and then evaporates. But there is one special case, and that's with frost. So frost is largely frozen dew. So dew drops form, and if the surface is cold enough, then they freeze. And but there's various types of frost, hoarfrost and things like that. But basically, it's frozen dew. And there is a case where, like in this picture, you see that frost is on the top of the dome, but the bit that's facing towards the sun has actually melted as the sun comes up and warms it. So what can happen is the sun is low and it's coming through this clear part of the dome, and then it's reflecting off the inside of the frost cap or ice cap. And that puts the readings up, and it can read too high, maybe by up to 30%. Then as the sun goes higher, it's hitting the outside of the frost, and then the readings go down and it's too low. So there are all sorts of strange effects that can happen. So this is an example of measurements made by FMI, Finnish Meteorology Institute, at their research center in Kuopio. And what they do is research into the effects of trying to keep the domes of instruments free of frost, snow and ice. So using various types of heating and ventilation and things to do that. So what we can see is that we've got a purple line, and it's actually overreading. So in the morning, and then at the point where all the instruments are cleaned, it goes back down to read the same as the ones which were already kept clean. So this is the example of it can read higher because of frost over the dome or partially over the dome. And then the blue one at the top, that is a pyrgeometer measuring the long wave thermal radiation. And that is actually also reading high until it's cleaned. And this is because of the fact that you actually have got a different thermal effect with a coating of frost on the top. It's not to do with light not getting through, it's actually purely thermal because it's a heat detector and not a light detector in this case. So what this is illustrating is that unless you can keep the domes clean, you can get very large errors. And what we want is the maximum uptime of good data. So one way of doing this, a traditional way of doing it, is to have a heating and ventilation unit. In our case, it's the model CVF4. And you can put any of our radiometers, the UV ones, pyranometer or pyrgeometers, inside this. It's completely waterproof to IP68, has a 5-year warranty. All the sensors themselves, all those different radiometers, they also have a 5-year warranty, and they're IP67. So what we have is a fan that is sucking air in through the bottom, and there's a coarse filter to keep out large particles, and then there's a fine filter, so that we end up with clean air is being swirled around inside and out over the dome. And this makes a little barrier, which reduces the amount of dirt and dust and other contaminants, could be pollen, for instance, that is falling onto the dome. It doesn't completely stop it, but it reduces it significantly, so you don't have to clean so often. But the other thing you can do is it has a heater that you can turn on, and when the air is heated, it's not a lot, it's only about 2 degrees, but it's enough to keep the dome above the dew point. So it stays dry because dew is not condensing on it, and therefore frost is not forming either. It will eventually melt snow and ice, and it will help to evaporate raindrops faster. So you don't have a problem with dew or frost, and it also helps keep a better uptime of other forms of, say, obscuration, whether it's snow or raindrops. So there's very little maintenance. All you have to do is periodically unclip the filter and change it. And it also has a pulse output. So it monitors the fan speed. There's a pulse that comes out, 5-volt pulse, twice per revolution. So you can connect that to a data logger and see how fast the fan is going. So this is sort of a bit what it looks like, that we've got air is being sucked in the bottom and it's being heated, and then it swirls around and it goes up over the dome, and that's what's helping to keep off dirt and dust and soiling. So in the picture at the top left, the 2 units to the right in the picture, those are the current ones, the CVF4 model, and the one to the left is the previous one, CVF3. And then the instrument that's further back in the picture is covered in frost, and that one doesn't have any ventilation or heating. So it runs off 12 volts DC, and you need the fan running continuously. That takes 6.3 watts. And the reason for that is because you can have dirt and dust falling on it at any time. And the heater, you could turn off when it's warmer and it's not going to get dew or frost, and only turn it on, for instance, when a meteorology data logger has worked out the dew point and saying, okay, we're getting close to the dew point, turn on the heating. But you can leave it on all the time. That doesn't matter. So, Victor, if you can give some of your experiences with using the CVF4.
Thank you, Clive. So when we're using the heater ventilator in the field and we're blowing the ambient temperature, the ambient air through the ventilator, across the body, and out the top through the dome, it's actually keeping the pyranometer at a constant temperature, not only keeping it clean, free of dust, free of dew, free of precipitation, but it's also letting the dome and the body stabilize. So we minimize the offsets, so the instruments are actually more accurate for giving a better solar radiation reading. Another experience that we have with the ventilators is in remote locations. We're not all fortunate like government agencies where we can have the sites manned, where we can clean these domes, do maintenance daily on the instruments to make sure that they're the most accurate measurements. So where we're in the deserts or in the Arctic conditions, or even in the middle of a forest, the ventilator is going to keep a constant flow, keeping the dome clean. And then, as Clive stated, using controllers and knowing the atmospheric conditions, you could turn on the heaters when the humidity is above, say, 80% and the threat of rain's there. Or if you have a tipping bucket and you know it's raining, you could turn the heaters on in certain conditions. Temperatures, when they get to be around 5 degrees Celsius, you probably want to turn them on. These are the situations where the ventilator is a benefit to the application for measuring this, not only the solar radiation. You got the pyrgeometer for the long wave radiation, and then we got the UV sensors. All our sensors have the same construction, and they fit into the ventilator perfectly.
Okay, thanks, Victor. So there is an alternative. Not everywhere in the world do you have problems with dirt and dust. It could be that you have a very clean site with clean air, or you have a lot of rain and it just washes off periodically before it becomes a problem. But a lot of places experience dew and or frost during the year. So you don't need the complete ventilation system to help keep off the dirt and dust. You need something to prevent the dew and the frost forming. So our new SMP12 pyranometer, it fits into the model range of SMP3, SMP6, 10 up to 22, going up in performance. So this is between an SMP10 and an SMP22. So the housing looks similar on the outside, same shape and size, but this one has got a built-in heater for the dome. So it's just below the dome on the metalwork, and it's on all the time. It takes about 3 watts, and it keeps the dome warm. Make sure it's always above the dew point so that dew and frost can't form. And of course, it will melt snow and ice after they formed. And of course, it will help to evaporate water droplets when the rain stops. But it won't do much to keep off dirt and dust. So that is something whereby you actually still want to have the CVF4, the ventilation unit, which also has the heating. But if dirt and dust isn't an issue, you can use this one. And so there's no moving parts, nothing to wear or maintain. This one also has a tilt sensor built inside so that you can see if the alignment has changed, whether it's still horizontal or not remotely. And because it may be, for instance, that something is knocked or a tower has moved in the wind or something like that. It also has a humidity sensor, because although all of these models are sealed essentially for 10 years with an internal desiccant to keep them dry, it's a possibility that, of course, you could get some damage done. Either it could get dropped or mishandled or hit by something, which might start to cause a leak. So this one has an internal humidity sensor. So you could say, okay, if the humidity gets to more than 80% RH, we need to go and have a look at it. It looks like there may be a leak and something's been damaged. So like all the others, this is IP67 and a 5-year warranty. But also, like all the others, when it's recalibrated at one of our service centres, we also replace the internal desiccant, even though it should last up to 10 years, just as a preventative thing. So it does look a little bit different from the normal pyranometers from the outside. So usually when you look at down through the dome of a pyranometer, it has a black disc about 20 millimeters diameter. That's what is absorbing radiation from the sun and the sky from all angles. warming up the top surface of the thermopower detector, and heat flows through it into the housing, and that generates the output signal, a few microvolts per watt per square meter of radiation. So on a bright sunny day, you might have 10 millivolts is developed by the detector. And then that is what is then digitized in the SMP12 analog to digital converter and all the other SMP models, and then it's processed digitally with temperature correction and things like this. But if you have one of these large detectors and you try and apply heating near to it on the housing, it destabilizes it. It takes a very long time for it to restabilize with changing conditions. And so it's not really practical. So SMP12 is different. It's got a very small thermopower detector. It's only a couple of millimeters across, which is actually the same one that we use in our Raison Plus all-in-one little monitoring system. So the special pyranometer and pyrgeometer that are on that, they have this detector in. So we've used it for a number of years. So it's small, and it's isolated thermally from the rest of the housing. So we can heat the housing, and it doesn't affect the detector. The only problem is because it's small, it's down inside, it can't see the whole sky, and we need to collect radiation from all directions. And so this is why we've got the small white disc, which is made of quartz, and that's a diffuser. So what it does is it gets light from all directions, and then it scatters it down towards the detector. It's very carefully designed in shape to get a good response of light from all angles. It's made of quartz, so it doesn't degrade with UV radiation from the sun, which various types of plastics do, PTFEs, for instance. And another advantage of this is that it's small. It's a small detector, so it can have a fast response. So, for instance, an SMP10 model with a big detector, that has a response time to 95% of 2 seconds. But if you can be less than half a second, under ISO 9060-2018, you can call it fast response. And this one is. Now, in reality, this only makes a difference when you're doing some research and you're looking at for instance, the effects of the edges of clouds going over. Because typically in meteorology, climatology, agriculture, you might only be measuring, perhaps taking a sample of the output every 3 seconds and then recording 1 minute averages, which you then might process into hourly averages or something like that. So this fast response time doesn't actually really matter for other than some specific research applications, but it does have it. It's just inherent. And because it's small, it also has very low thermal zero offsets. So if you don't have an issue with soiling, but you do with dew and frost, then the SMP12 could be the solution you want. If you don't have a problem with anything, soiling, dew or frost, or it's so infrequent that you're not worried about it, then of course you can just use an unprotected pyranometer, an SMP10 if it's a digital one. So we also have another heating and ventilation unit. We have an instrument called the CNR4 net radiometer, and this measures the total radiation balance and is very popular in all sorts of resourcing, water resourcing, agriculture research, using on ice fields to see the effects of global warming and things like that. And so this has got 4 radiometers all in the one housing. So we've got a pyranometer, entry level one, looking up and down, and from the ratio of the 2 signals we can get the surface albedo. And then we have 2 pyrgeometers, one looking up and one looking down. So we get the long wave radiation coming in from the atmosphere, the long wave radiation coming up from the surface, the short wave radiation coming from the sun's sky and reflected from the surface underneath. So it gives you all 4 parts of the energy balance. But again, we can of course have all these effects, the dirt, dust, and dew and frost on all 4 of these detectors, because you might have dirt blown up from underneath, and you can actually also get, due to temperature effects, you can get frost and dew forming on the ones below, not just the ones above. So we need to do something about that. And so we do have a heating and ventilation unit for this. It adds on to the back of it. And this is working on the same principle. It's sucking air in through a filter with a fan, and then it's blowing the clean air along the housing, and it comes out over all 4 of the instrument domes and windows. And again, it's got a heater that you can turn on, and again, you can measure the rotation speed. So again, it works from 12 volts DC, like the pyranometer one, CVF4. It takes 5 watts for the fan, which you want on all the time, and then 10 watts for the heater that you can switch on when you need it, or leave it on continuously. It doesn't really matter which. And so this is an example of where these sort of things are used. So this is an ICOS tower. So this is about measuring the energy balance and things over forests in Europe. This one's in Sweden, and it's a very high tower, so you can't get up there to clean it. And so that's why they specify having the heating and ventilation units. And Victor, if you would like to just say a little bit more about these sort of special applications.
Yes, Clive. Most albedo readings, or when we want to take measurements in the field, meteorological recommendations is at a 2-meter height. So it makes it very simple for us to go out there and clean the sensors. But in applications like this, on towers at upper levels, not only are they going to be at 10 meters, maybe 50 or 100 meters in height, you also need to get the instruments away from the tower so you don't see any effects of the tower radiating back, scattered back onto the sensors. That's the reason for the ventilator, the heater, to keep the domes clean for accurate measurements, keep the dew off as well. The constant air blowing across the CNR4 actually helps also increase the accuracy of this. Like I stated earlier, making sure the body and the domes are the same temperature. But the instruments on the CNR4 have only a single dome. They're Class C sensors. But when you do blow air across these sensors and you are keeping the offsets lower, they will give you a much higher grade. That they can't be labeled as a Class B, but they will give you data as well if they work, because of the effects of the heat of the air blowing across the units. When we have these applications, each of our fans come with a screen filter and a mesh filter. And the mesh filter is there for a reason, keep the dust out of it. But that mesh, like your air conditioning or any other filter you have, is going to get clogged. And then once that clog starts, you're going to have very low airflow going through, and then the ventilation doesn't even seem to work anymore. So what we would always recommend in these type of applications is only keeping the hard screen in, but remove the mesh filter, because the amount of time you would have to go up there monthly to change out that mesh if you're in a very hazardous or dust environment. Programs that use this is agricultural, climate research. We see it with the Ameriflux program here in North America, the Euroflux program in Europe, the ICOS towers over here in Sweden for the research. Emergency response. You need to know this for stability classes, because heating effects under light winds is going to give you different wind patterns. And one thing that we didn't talk about on here, and we don't have any pictures of, is onboard ships for research across the oceans, where they do need ventilation to keep the sea spray off and making sure that the domes stay clear.
Yeah, so thanks very much, Victor, and thank you everybody for your attention and listening to us, and we'll hand you back to Danny.
All right, thank you very much. We're now going to move into the Q&A part of the webinar, and just before we get started with that, just draw everyone's attention to the handout section on the right hand side. You'll find a link to some extra resources about what's being presented today. Victor, we'll start off the Q&A. I just don't know if you mentioned just at the end there about the onboard ships. Do you want to talk a little bit more about that, perhaps?
The vast majority of the Earth is covered by oceans, and organizations in North America like NOAA, they have research vessels, and they monitor atmospheric conditions as they go across the oceans across the world. And on these ships, they'll have the pyranometers, both long and short wave. And they can't get to them all the time because it's a very moist environment. You do have a lot of sea spray that comes up. The domes are going to be impacted by the moisture, by the sea spray. And salt on the domes, when the sun is baking on them, over time, it may actually etch the glass domes. So when you have the airflow blown across with the ventilators, it keeps it very stable, but it'll actually blow off that moisture, so you don't have the damage to the domes. This is the reason when they do these research experiments, they'll have both a pyranometer with the heater ventilator.
All right. We've got some good audience questions that have come in. It's not too late to send in those questions, so please do use the Q&A box on your right-hand side to send those in. Any we don't answer, as we said in the introduction, we'll be answering via email. So, Victor, perhaps you could comment a little bit more about where the best place for these to be used. What's the best environment? And I know you've got a couple to show us, so maybe I'm just going to bring you the camera up onto big screen so we can see slightly better.
So when we talked about a lot of applications during the presentation, and we talked about the poles with snow cover, anywhere where you would see dew or frost, rime icing. There's not one perfect place on our planet that is not going to be affected by atmospheric conditions. So when we have our ventilators and the air is coming through the bottom, as you said, it has an RPM motor in here so you can monitor the fan speed. It's going to consistently blow the air across, and as it blows across, it's going to keep these domes clean. At the poles, snow builds up. It's going to melt the snow off to get the dome clear so it can get the solar radiation. In the tropics, very moist, lots of rain. It's going to give dew spots or rain spots on there. The fan will blow that off. So again, the instrument will take accurate measurements. But say between 25 and 45 degrees latitudes, north and south, we have nice climate, but we do have morning dew. And sometimes that doesn't burn off for a couple of hours after sunrise. Having the heater ventilator will eliminate that. So this way your instruments will be accurate right at the break of dawn.
What about sort of ongoing maintenance? I think you mentioned in the presentation about sort of 5-year warranties and things like that. So how can people buying these products ensure that they're staying, and the accuracy of the measurements is staying solid throughout the lifetime of them?
The pyranometer is going to be a constant measurement, and as you're monitoring your data, you'll see that there's no discrepancies day after day or maybe year over year. We recommend once every 2 years to send them back to us for recalibration, where we recheck them to make sure that they're still stable. They are completely sealed instruments, and on our instruments with the 5-year warranty, we have a mean time between failures of greater than 15 years. We also have pyranometers that date back into the 80s. So we're talking very constant, accurate data from these sensors. With the new CVF4, we made a better fan. It's now IP68 rated. It's blowing air through the bottom and then out. These fans themselves are very rugged in construction, made for really nasty environments. Also, the reason why we give a 5-year warranty on these units, that they're going to work as we suggest and how it's supposed to be over time. In optimal conditions, these fans will go anywhere from 6 to 10 years. But when you get to the extremes, down to minus 20, minus 30 degrees Celsius, sometimes worse, or up to 40 degrees Celsius, and during the hot summer climates, and you have these ranges, it puts stress on moving parts. That's going to, over time, cause these things to need replacement, just like an engine on your car. Nothing lasts. Anything that moves will never last forever. Why we have an RPM motor on these, or RPM monitor, it's a pulse output you monitor. It's going to give you a constant flow. So you're going to have that at your location. As those RPMs go up and down, you'll know the integrity of the fan, if it's working or not, or how good it's working. When the RPMs increase, that means the fan is spinning faster, but that's because there's no resistance. The filter is clogged, and very simple to take off, look at it, replace it, put it back on, and you'll see instantaneously resistance on the fan, and then the RPMs are going lower. If for some reason the RPMs drop off to 0, that means your fan's not spinning, and then it's time to do a quick replacement. And it can be done in the field, or it can be done at any of our service centers.
So you're obviously having a very close relationship throughout the sort of lifetime of the products with the customers if you're constantly maintaining and monitoring the maintenance of them.
Yes, we have offices in almost all countries across the world, and we do try to work very closely with all our customers and answer any questions and make sure that everything's working to the best, our standards, so they have the best data available.
Yeah. There's a question here about the accuracy and comparing it to the other products. They don't specify what products they're using, but they're just asking how does the accuracy compare to other products on the market?
During the presentation, we talked about the different classes of the pyranometers, and having the different classes they have a range on how accurate they're supposed to be. But the unit itself, the fan with the heaters, as it blows the air across, will keep the pyranometer to the highest level possible, clean and same temperature between the body and the dome. Our unit has the fan, it's on the back side. It blows the air in, and it has a centrifugal force around to clean the entire dome as it goes up. There was a slide in the presentation that showed this process. Other products on the market have the fan directly below, so the air comes straight up. And also on the presentation earlier, you would have saw our original ventilator, where there was always a spot of snow or dew that was on top of the dome, and that's just because of the way the flow is going up. It's just a pyramid effect. It just can't get all of the debris off. That's why we changed our design about 8 years ago to have this circular force. When these things are on mounting plates or on trackers, the filters are very easy to replace. Just as you saw, I just pulled it off. The old style on the bottom, you would have to undo the entire unit, take it off, take off the filter, and then put everything back on, go through the leveling process. So we try to make it as simple as possible in the field, so this way these maintenance is relatively easy.
So if anyone watching wants to demo them, see them in action in the field, what's the process for how they would go about that?
You call up your local representative. We have videos, we have brochures, and we also have a lot of online data sources from government agencies which can show the effects of how these instruments are working within a controlled heater ventilator with the pyranometer, or just on its own. Perfect.
I've just pinned to the top of the handout section a link there, which will take you to AZO Sensors. You'll find all of the other content that's relevant from today's presentation. We've got through the questions. Victor, is there anything else you want to quickly demo or finish off with before we end the webinar?
All of our parts are replaceable. So if it ever happens where there was a hailstorm or the hurricane that just hit Florida as it's moving up the East Coast, things get damaged, and we are able to replace everything. We have things in stock. So very simple to come off. Domes can be replaced through the service center. Recalibrations, just call up your local rep, and we'll work with all the customers to making sure these instruments are always working as expected.
Perfect. Yeah, I think we'll wrap things up there, Victor. Thank you very much to you. Thank you very much to Clive for the presentation earlier, and a big thank you to the audience for taking the time to join us today. Survey will appear on your screens once you leave the webinar room, so please do share your thoughts and feedback there. And if you want to find out anything more about what's been presented, then do visit the OTT website or follow that link in the top right corner. Right, that's about it. Thank you very much, and have a great rest of the day.